Like you, I have a lot of questions, more every day. What's the weather going to be like tomorrow? How did the Big Bang unfold? How many chocolate chips can I scarf from that bag of trail mix before anyone notices? But my brain might start to overheat if I tried to answer all the really complex questions I have. Fortunately, supercomputers can do the heaviest brain lifting for me.
You can think of a supercomputer as the ideal environment to run experiments to understand any part of the universe.
And they're getting more powerful all the time. Does that mean my most challenging questions will all be answered one day? Well, I can hope. I'm Seth Shostak.
I am Molly Bentley, and this is Big Picture Science, produced at the SETI Institute. In this episode, the race to develop the super-est supercomputer is as competitive as an Olympic sport. Every few months, engineers crown a new processing system the fastest or the smartest, and now they're reaching for computing heights so lofty, well, they require a new vocabulary. Exascale is the new benchmark, and it is just around the corner. But a dark horse candidate is threatening an upset. Quantum computing is faster than all these machines. Will it make them obsolete? It's Supercomputer Showdown.
In case you were wondering what the stakes are in building the world's most powerful processing machines, well, get a load of their names. I mean, they read like the cast of a superhero blockbuster. Summit, Sierra, Titan, Aurora, Frontier, and that's not to be confused with Frontier.
And those are just some of the U.S. supercomputers seeking domination. China has the powerful and mysterious-sounding Tianhe 2A supercomputer, while IBM Germany flexes computer muscle with its SuperMUC. Well, what puts the super in supercomputers, and why do we need these triumphs of technology?
We'll answer all of this and explain the supercomputing pecking order with a little help from a carbon-based computer operating in salt water that we call a brain.
I'm Katherine Reilly. I'm the Director of Science for the Argonne Leadership Computing Facility at Argonne National Lab.
Her lab has a horse in the supercomputing race for sure, and we'll come to that. But first, why should we care about supercomputers? Talking about how powerful they are without addressing how they help us, well, it's like marveling at the height of skyscrapers.
We need supercomputers in order to explore questions and answer problems that we have in the real world that we cannot answer other ways.
Okay, well, that's reassuring, because supercomputers as a staple of science fiction, well, they're not usually doing humans a favor. Instead, they're menacing machines focused on world domination, which means we humans either end up incinerated, enslaved, or harvested for our battery power.
There are fields now. Endless fields where human beings are no longer born. We are grown.
But we're pretty sure that's not what motivates this new crop of superprocessors. Engineers are building machines to tackle our toughest questions. Most of us are familiar with the prefixes mega, giga, and tera with our own computers. But it doesn't stop there. Today's supercomputers are in the elite club of petaflops, that is.
Petaflop is a unit of measure. It tells you how many bits of mathematics you can do in a second. So it stands for floating point operation. A floating point basically just means a decimal number, like 2.0 instead of 2. And how many operations of those can you do per second? And a peta is 10 to the 15th. So that means you're doing 10 to the 15th add, divide, multiplies in a second.
That's 1,000 trillion operations per second.
And another way we like to describe this sometimes is imagine every single person on Earth doing thousands of mathematical operations in a second. And then you got your 1 second of a petascale system.
Now, knowing the power of a petaflop computer, let's go meet one. Not just anyone, the currently most powerful supercomputer in the world, Summit.
It takes 2 human brains to pose all the questions we have about supercomputers. Reporter Emma Bentley, my sister-in-law, and yes, science reporting runs in the family, met me at Oak Ridge National Laboratory in Knoxville, Tennessee. So, Emma, now we stepped into this data center. But it's not just any data center.
Yeah, this is just amazing. I just love the racks and racks of green lights.
Right. This is Summit. This is a supercomputer.
I'm standing right. In fact, I'm going to touch this computer. I hope I don't get electric.
I don't know if you're allowed to do
Am I allowed
that.
to do that?
Yeah.
Okay, that's really cool.
This is really profound because when we think of computers, we think of them getting smaller and smaller. And we're looking at rows and rows of these cabinets. How many rows? 1, 2, 3, 4, 5, 6, 7. 7 just here, but then there are infinite, well, not infinite, but a number of rows, another dozen rows down that way.
And there's 180 miles of electrical cables. It's all being cooled by a swimming pool amount of water over our head and cooling it inside the cabinet, cooling every single one of those little microchips, just chilling it down and making sure it's at the right temperature to work, apparently.
When we go to the very end here, if there is an end, yeah, it does look like it does end.
This is possibly the most stylish supercomputer.
Yeah. Why do you say that?
Well, I love the blue, retro, very 80s, very mountainous. It is called Summit, after all. They've got a mountainous logo. And it's sort of chevrons down the side of the computer cabinets.
Yeah.
It is terribly, terribly impressive.
Yeah. Well, Katie Bethay has been our tour guide for much of our day here at Oak Ridge.
We have 200 petaflops of computing power here, and so just amazing to imagine, the science that we're able to produce in such a small space. Flop per square foot. It's really efficient and compact. They talk about the density of the computer. Summit is very dense.
Is it just my imagination, or does this room have that new computer smell?
It sure does. It really does. It has that clean, sterile, mechanical smell.
So some examples we use supercomputers for are designing better drugs to treat cancer, to find the early precursors to diseases, right? So what are the first ways that you might develop Parkinson's disease? We use them to design safer buildings and safer materials, right, to build those buildings out of. And we use them to understand even the weather and the climate going on around you.
Supercomputers are useful for wide areas of science and engineering. It's often to solve the most challenging problem in a particular domain. I'm Jack Wells from Oak Ridge. My role is Director of Science of the Oak Ridge Leadership Computing Facility. Summit is a large supercomputer, 256 cabinets. There's additional cabinets for the parallel file system. Each of Summit's cabinets has 18 nodes. And each node is actually a fairly complex thing. It's a node on a network. The network has a topology or a connectivity of a tree structure.
What is the super in supercomputer? Why is it bigger? Is it faster? Is it better at doing those calculations? Or is it something to do with the architecture?
So to be sure, people want answers to the questions they are asking. They want it back fast. So speed is an important thing, but it's also dealing with a sense of parallelism here. So getting multiple computers to work on the same task coherently, right? So all these components, it's not so much one particular thing. We deploy supercomputers here where they have an architecture with enough memory bandwidth, computing power to do things that can't otherwise be done, that would actually offer a new capability to a science or an engineer.
So if we were to open up the Summit cabinets right here, and I'm not proposing to do that, what would we see? And if you looked at that cabinet, would you be able to say, that's a supercomputer? And could you tell just by what you saw inside?
You would have to take a very close look, and just looking at the front of the cabinet might not be enough because you would just see a rack of 18 servers stacked on top of each other. But if you turned around and look at the back of the cabinet, if you saw the networking, you might be able to recognize that, these cabinets are connected with very high bandwidth communication technologies that would effectively enable them to operate in concert together on individual tasks.
So those connections are what are important. The networking inside the supercomputer is what's key.
It's a very key aspect. This is much more than just a collection of 256 refrigerator-sized cabinets, but it's really one unique machine.
So supercomputers can do things that we can't afford to do normally. So one example of that would be if you want to have a safer car, right? We have safe cars today because of supercomputers. You can crash a car in a computer as many times as you want. You can do that thousands and thousands of times. But an experiment to crash a car and see how safe it is might cost $1 million, right? So do you have hundreds of millions of dollars to keep crashing a model of a car? So this is a good example of a type of problem that would just be cost prohibitive to do otherwise. But there's other categories of problems, like problems that you could never do in a lab. We cannot have a sun in a lab. We don't have the ability to contain the temperature or the reactions of a sun and put it in a laboratory. So we can't understand how stars or our universe have evolved, right? So a supercomputer can also provide a place to do experiments that you just could not execute normally.
Computers have gotten faster over the years because the CPUs, the central processing units, those are the chips that do the actual computing, they've been subject to Moore's law, which means they more or less double in speed roughly every 2 years. But supercomputers are actually improving faster than Moore's law, and they do that mostly by having more processors on the inside.
A supercomputer speed up is a lot more than just, say, the limitations of Moore's law and what you might see in your laptop, because a supercomputer is built of tens of thousands of small computers. So it's not just how capable those individual computers are, it's how we make all of those individual computers talk to each other and be really efficient at talking to each other that really defines what a supercomputer is and leads to these bigger jumps in speed up than we would see just by looking at, say, your GPU or your CPU in your laptop.
For a comparison of how the CPUs and GPUs of your laptop stack up against a supercomputer, Emma returns to the room that holds Summit.
This is massive. This is a massive, massive space. It's a little bit like Indiana Jones and the Temple of Doom, where they store the Ark in this enormous
Warehouse.
So it is a warehouse full of activity.
Yeah, I mean, people often think of computers shrinking in size, and we're able to have a tremendous power in our cell phones, and we carry that around and high degree of mobility. But here we're trying to assemble a large computer where we can make these different components work cooperatively in concert. And our ability to solve problems is often limited by the ability to field a computer like this, to have a big enough room and enough electricity in order to power the big infrastructure. This is what's needed in order to do bleeding edge solutions in science and engineering.
Lots and lots of green twinkling lights. What do all the lights mean?
So those lights are just associated sort of with the power on state with the different servers that are in each cabinet, the different nodes. Each node has about 8 processors per node, and that's the node on the network. 2 of them are conventional CPUs, and then 6 are GPUs, or graphical processing units, that originated from the graphics industry, like playing computer games, but now these GPUs are very much a feature of running data-intensive applications and high performance in modeling and simulation also. There's over 9,000 CPUs, and there's over 27,000 GPUs in this computer.
If I was a researcher coming in here with a question about life, the universe, and everything, how would I get my question, my application, and my code into this computer and get the answer out again?
So everyone uses the computer over the wide area network. So people log in over the internet, and they have credentials and a 2-factor authentication, and then you can use it just on your own laptop wherever you are from around the world, right? Yeah, we're an open science supercomputer. We do have stringent security, but this is open for use.
One question that we tackle is how to design better drugs to treat not just a particular disease, but maybe your particular disease. So if you imagine there are millions of different chemicals out in the world, and the way a computer speeds them up is it can look at all of those thousands of chemicals and all the different possible combinations of all of those different chemicals and do computer tests to see how effective they might be at treating a particular disease. And that would take a human many, many times longer to do than a computer would do.
So what you're saying is we'll just sort of simulate the lab in the computer and save the cost of building that lab and having somebody wash all the glassware.
Right. A supercomputer is basically a simulation environment. It is a way to represent part of the real world and answer real world questions inside it, but be able to answer those questions much faster than we would otherwise.
To say the obvious, supercomputers can do things enormously faster than ordinary computers.
Yeah, well, they can. And as we've heard, they're like 1,000,000 times faster than my laptop, and I think my laptop's pretty fast.
What puts the super in supercomputer?
Well, for the supercomputers, what they do is they say, look, we're just going to put lots and lots of, if you will, individual computers together in one box, and that gives it the processing improvement that you can't get any other way. Then you also need what's called interconnectivity. In other words, they have to be able to talk to one another. And if it takes them a long time to talk to one another, if they're slow at doing that, then you may lose some of the speed increase. So you need both components in a supercomputer. And if that's a slow connection, right, then, it doesn't matter how fast those CPUs are, because if they can't talk to one another fast enough, they can't work together as a team. And by working together as a team, the overall result can be much quicker.
When you have all that power, when you have all that speed, you need to keep the system cool. And you heard references to the role that water plays in keeping the supercomputer from losing its cool.
Yes, that's a critical thing. But that's, in fact, not new. I mean, the big digital equipment computers that appeared in the 1990s, they had plumbing. I'm talking about literally plumbing for the water cooling to keep, them operational. Otherwise, you have to spread the parts out over over a big space so they all stay cool. If
like
you do
laundry,
that,
like putting your laundry out.
Yeah, that's
spreading
right.
it all out so the sun can get to it.
Exactly. And so they'd had to do that, and that would slow the computer down, because now it takes a certain amount of time for a signal to get from, a bit to get from one part of the computer to the other. You want to make it as compact as you can make it, and that means you've got a heat problem.
What's the role between all that water used to cool the supercomputer and building an energy-efficient computer? Because it would seem as though it's not energy efficient because it's requiring all this water to keep it cool.
But the point is, if it's efficient, it requires less water.
Well, you would think that having a multi-petaflop computer like Summit would mean never needing another computer ever again. But PETA is a rest stop. It's a chance to catch our breath in the climb past the current Summit. The race to achieve what comes next is next.
They're big, they're brainy, and computers are only getting brainier. Speaking of brains, how do ours compare? Well, we'll find out. It's Supercomputer Showdown on Big Picture Science. If you're in the movie business, you probably don't make a habit of bragging about flops. But in the computer industry, racking up flops is desirable. It's the gold standard measure of speed. Floating point operations per second. How many additions, subtractions, or multiplications your machine can do in a second.
We're talking about the ever-growing power of supercomputers in this episode and the sort of problems that they can solve. When machines capable of more flops come along, the older machines with less flops, sometimes only a few years old, are replaced with these newer, more supercomputers. It's out with the old, in with the new, with a fast turnaround.
Katherine, this rate of growth being so fast, that strikes me as something that would be kind of discouraging, wouldn't it? You build this supercomputer, and then 2 years later, you could build one that's 10 times faster, whatever it is, and, it seems like you wasted your time building the earlier one.
I can see why you might think it's disheartening, but overall it isn't, right? So the design of these systems takes into account what kind of science we want to do on them over the course of they live for about 5 years. And so we really consider that as we're building them and designing them and helping scientists exploit them. So there's normally even more than 5 years worth of work we want to get out of these systems, even when in the 5 years is up. But often It's that we can build a more efficient machine, an even more efficient machine after some numbers of years. And that drives sort of this reasonable argument to build something bigger and something more capable.
And sure enough, while Emma and I were at Oak Ridge National Lab, Jack Wells took us down the hall from the room containing Summit, that 200 petaflop computer that is currently the most powerful in the world, to another room that had the appearance of a going-out-of-business sale at your electronics store. Disassembled black cabinets were piled on the floor, dozens and dozens of hard drives heaped in massive cardboard boxes. These were the parts that once made up Titan, the predecessor of Summit. The Oak Ridge folks were clearing the room for Summit's successor, Frontier.
And this is where Titan was. Since beginning in 2012 until just a few weeks ago, we operated the Titan supercomputer here for our user program. We've just decommissioned it, and within 3 weeks, we disassembled it. And so what you're seeing now are some of the boxes and the parts that still haven't made their way yet out of the data center. The reason we're doing that is, of course, this data center is where Frontier supercomputer is going to go. Frontier will be Oak Ridge's first exascale supercomputer. Initial delivery in 2021, with users having access in 2022.
Okay, so let me ask you, what's the difference between Titan and Summit and the new supercomputer of Frontier, which is exascale? What do those scales mean?
Titan was deployed in 2012 and was the most capable system in the world at the time, number one on the top 500 list, with a peak performance of 27 petaflops. Summit is the most capable supercomputer in the world today and also the most energy efficient. It's a 200 petaflop supercomputer, 200 million billion operations per second. And Frontier will be our lab's first exascale supercomputer. That exa is a prefix that means a billion.
So we have a new prefix. We go from peta to exa.
That's right.
And I think the one after that is zeta. Are you ready for the era of zeta?
No, we're not ready for the era of zeta. And that's off into the future, and that will be defining a new frontier, right?
But it seems like there's a lot of equipment here. Why couldn't you use some of this equipment, or are you using any of this and refashioning what came from Titan and putting it into Frontier?
We're not. There's many reasons you would choose not to do this, but fundamentally, this older supercomputer is no longer energy efficient to operate at the scale. The new supercomputers we bring in are state-of-the-art in energy efficiency, and that's very much a limiting aspect of what we're doing. How much energy can we deploy and how much can we get out of it?
And then what happens to those hard drives?
They're recycled, and whatever is valuable in them will be extracted and reused.
The National Lab in Knoxville is not the only facility vying for exascale. Katherine Reilly says you should expect to say hello to the supercomputer Aurora in 2021.
So Aurora will be 1,000 times a petascale computer. And that's where our goal is. Our goal is to exceed an exaflop.
Let's talk a little bit about the competition, because Argonne National Laboratory, where you are, is not the only place claiming that they're going to get to exascale computation. Oak Ridge National Lab says they'll soon bring their exascale contender, Frontier, online. Why do you think Argonne will reach exascale first, or do you think that? And does it matter?
From a pride perspective, it matters. We are certainly pushing. We have had the go-ahead on our project longer, so we've been developing it a bit longer with our partners. But it absolutely is a race. But overall, we are partners with Oak Ridge. We both run leadership computing facilities where these resources will be deployed. So while I want to be first, and I think we will be first, it's mostly a race of technology at this point to see who gets it on the floor.
All right, so what kind of questions would it be? I mean, if it's 1,000 times more powerful, that's not going to help me with my word processing or my spreadsheet, but presumably it would be able to address a different category of questions than the petaflop computers?
The special thing about Aurora is it's capturing in one system a different way that people are trying to tackle their science questions today. So we used to do problems, and still do some of them, answer questions by sort of just kind of running, right, this little simulation of the universe, right? We would say, I want to study this star and, let the star percolate, right, and burn for a while within the computer. But the way we ask our science questions today and moving into the future is a lot more complicated. And we have more data coming in from experiments and coming in from other simulations and coming in from the world than we really know how to tackle in many respects. And Aurora is one of the first attempts to build a system capable of tackling doing simulation on the real world and analyzing that real world data, and maybe even using really clever techniques like machine learning to innovate how we're managing and learning from that data.
What about the kind of classical problems that you hear about, if you delve into this at school, like the traveling salesman problem? Now, you might think that the problem they have is finding a good restaurant at a reasonable price, but that's not it. I mean, if they got to make, 50 different calls in 50 different cities, what route should they drive in order to do that? That's apparently a very difficult problem to solve.
It is, yes.
And maybe it's not worth putting Aurora on that, but, are there problems that we just never even thought we could address that Aurora will be able to solve?
That's a very good question. I think one area that we are trying to help and an area that Aurora could really start contributing to is maybe not the traveling salesperson problem and that kind of graph challenge, but even trying to understand the flow of traffic, right, in your city, and how do you manage your commute, and how is your commute impacted by the weather that day, and whether there's a sports game. And that may seem like, well, I know the answer to that, right? I know when there's a sports game, I can't get to work, so I don't need a supercomputer to tell me that. But if you have models that can help you predict things like traffic, similar to ways that we predict weather, that might help city planners design better cities.
So in some sense, these really massive computers, these exascale computers, it isn't necessarily that they're addressing a problem that's terribly complex. It's maybe a problem that's, now we know how to solve it, we just don't have time in the future history of Earth to solve it with my desktop computer. I mean, it's sort of like I know how to solve crossword puzzles, but if the crossword puzzle was, the grid was a million squares on a side, I'm just never going to solve that one. Is that a fair fraction of the problems that these big computers are designed to solve?
That's absolutely true, yes. And what we call it is time to solution. It's one thing to get an answer to a science question in 10 years. It's going to have a lot more impact on you if we can get an answer to a science and engineering question tomorrow. And that's how we can make really rapid progress on doing things like improving the quality of people's lives, right? And that can even be from your car to how you're treated at the doctor's office.
Dr. Reilly says Aurora is slated for 2021, and Dr. Wells says Frontier will debut at the end of the same year. But the world's first exascale computer might not be American. The race to reach exascale calls to mind another historic all-out effort to be first.
This is often described as a race, and certainly it is. At least the journalists have been describing it that way, and the tech watchers. And it has been likened to the race to the moon between the U.S. and Russia. And I'm wondering what's at stake? Because in the case of the moon race, it did matter. It was a matter of national prestige and also, in some cases, we thought, security and defense. What's at stake here, and does it matter who gets to EXA first?
So it's a wonderful question, and it can be approached from many different perspectives. I will say it does matter in my mind that we have the ability to do these first-of-a-kind projects and to do them effectively. Being first or second surely does matter because we all want to strive and to achieve and to be associated with a winning team. The ability to lead the world in information technology globally is also at play here. Because of the role that energy efficiency is playing in information technology today, it's actually a time of change. The old ways of architecting these systems have to change to become more energy efficient. And so a lot of things are being relearned.
So on the horizon, we see computers more powerful than anything we can imagine. Although at this point, maybe you can imagine them. Woven into some of those capabilities is another technology that is growing fast and poised to become even more powerful: artificial intelligence.
There are a lot of technologies that improve AI, machine learning and its subset deep learning, and natural language processing, all, for example, letting machines get smarter without human intervention. So we have to ask, will the next generation of supercomputers be true thinking machines?
For perspective, Seth grabbed a quick overview of human versus machine smarts.
I'm Jeff Hawkins. I am the founder and principal scientist at Numenta, a company that studies the human brain from a neuroscience point of view, and we also work in machine intelligence.
Jeff, it is predicted by people who work in artificial intelligence that we'll soon have generalized artificial intelligence. That is to say, a machine maybe 50 years from now that can do anything cognitively that a human brain can do. What do you think? Is that likely?
I do. The real question, though, is how would we get there? Today's AI is not intelligent at all. Really, it's very dumb. It doesn't understand anything about the world. The question is, can we get to truly intelligent machines by doing more of what we're doing today, or do we have to take a different approach? I'm a firm believer that we have to take a different approach, that the human brain is the only thing we really know that is intelligent. We have to understand first how it works, and then we can build machines that work on the same principles.
Let me challenge that a bit. You say that we have to understand the human brain before we can build a smart machine, but people didn't understand birds before they built flying machines.
That's a misconception. The Wright brothers actually did. They owned birds, they studied birds, they put them in wind tunnels. Two things they wanted to learn: how birds control flight and how the wing shapes affect lift. They then understood that they didn't need to use the bird's method of propulsion. But to say they didn't understand birds to understand flight is not true. They did.
Okay, so you say we have to understand the human brain. Are we anywhere close to understanding the human brain? You can read that the human brain is the most complex thing in the universe, which sounds to me like it might be very hard to understand.
Well, that is the general belief. I've been doing this my whole life, studying the human neocortex. And I can tell you that in the last about 8 or 9 years, we've made significant progress on this, very significant. But the human brain is not something that we can't understand. It's just something we didn't understand. But it's not fundamentally not understandable. And so we now have a very good idea about the basic framework of how we think and what thinking is and how we store knowledge about the world in the human neocortex. What today's AI is doing, what is called deep learning, and it's a very simple technique. It's just a classifier. It recognizes patterns, but it knows nothing. Absolutely, to recognize a picture of a cat, it doesn't know what a cat is. It just says this picture is similar to another picture I saw, which was labeled cat. There's no knowledge there. And this is a little discussion about AI. If you go back in the history of AI, earlier attempts of AI worked on very different principles. People want to understand how knowledge is represented in the brain or in a machine. And they came to the conclusion that knowledge representation, is how you represent common everyday knowledge in a computer, was the hardest problem of AI. Today's AI doesn't do that at all. It has no knowledge. They just avoided it. But to really create intelligent machines, the machines have to understand the world.
So Dr. Hawkins does not think we're close to understanding the human brain well enough to duplicate it in a machine. But the more powerful the machines, the more powerful the AI technologies that run on them become.
Today in medical offices, there's a big challenge in maintaining records from our patients, right? And these are often text-based documents, some handwritten, some typed. There's huge challenge with medical records because when you look at it in total, there's so much that no human can actually read all the records in order to extract information.
It's an overwhelming amount of data.
It's an overwhelming amount of data. And today you can use an area of computer science called natural language processing to effectively have a computer read those documents and extract information out about what is being learned and what may be hidden in the volume of data to create new hypotheses for new trials or understand what is or what is not being effective. So this is a brand new area of medical records, health data sciences that's growing really quite rapidly.
Artificial intelligence that is employing deep learning or any kind of machine learning seems to be very power hungry. Not power hungry like dominance in the world, but it requires a lot of power. It requires the computing power of a supercomputer. And why does machine learning and deep learning require so much power?
It is very compute intensive. So these methods become much more effective the more data you can expose to them, right? So you want to be able to bring large training data sets, and the architecture of Machine Like Summit is very well suited to take on these tasks.
Are we getting close to simulating the processing power of the human brain?
I think that's still very far away. The processing that's done here is very structured, and the deep learning neural networks they're often using this word neural networks. They're not meant to be biomimetic in any sense or to describe the neural architecture of the brain, but they do have the ability to perform certain tasks that result in learning. Also, I would say this supercomputer uses a tremendous amount of electricity. The peak that we've measured is about 11.5 megawatts. The human brain, I've been told, consumes about 25 watts. So there's a whole lot to be learned in terms of how efficiently information can be processed by thinking about the contrast between those two figures.
25 watts on a good day. Yeah. But before coffee, who knows, right?
Lots of coffee is consumed around here, yeah.
While they're incredibly powerful, these computers, they don't have the same kind of interconnected capability that our brains do. So they're not thinking like you or I are thinking, even though they can probably almost certainly process certain types of data faster than we can process that data.
I certainly hope you're not whistling in the dark here, Katherine.
No.
But that does generate another question, and that is, maybe these machines, we ask them specific questions, they come back with answers, but maybe they come back with suggestions for new questions. Maybe they give us insight into what we should be doing with these machines.
Yes, and actually this is what we really hope out of generations of systems like Aurora. We have new and emerging ways of looking at this huge quantity of data we have. Some of this is climate data. Some of this is the data of everything that's going on in the city that day, from weather and traffic and local events. We are right now building capabilities into these systems to explore this data, help us find patterns, maybe even discover patterns we didn't know were there. But it still relies on the person to say, does that pattern make any sense? Is it a useful pattern? Is that pattern meaningful or not?
Okay, supercomputers aren't yet artificial generalized intelligence comparable to a human brain, and that means that I, for one, still have a job. But achieving exaflop capability and building a sentient machine are not the only milestones along the scenic and spectacular road of computer evolution. Another was reached while we were putting together this episode, and that's next.
It's Supercomputer Showdown on Big Picture Science.
Yes, the supercomputer race is escalating, but a giant leap for computers was recently claimed. The night before Molly and Emma went to Oak Ridge National Laboratory to talk to Jack Wells about the Computers Summit and Frontier, they heard that researchers at Google had made a breakthrough by achieving something called quantum supremacy. Okay, first, a translation of that, please.
What they claimed was that they were able to finally solve a problem with a quantum computer that would otherwise not be solvable with a traditional computing technology like what we deploy today. So that's what quantum supremacy means.
It's hard to overstate what it would mean to have a true quantum computer, a machine that's really been the holy grail for decades. But all we knew at the time of our visit to Oak Ridge was that this odd-sounding milestone had supposedly been reached. We asked Dr. Wells to comment.
So I'm familiar with that work to the extent that the team came here to use Summit and simulate a quantum computer. This notion of quantum supremacy really means that a quantum computer can do a task much more quickly than a classical computer can do. And they wanted to benchmark it against today's most capable supercomputer. But the task that they're doing is really validating a quantum computer. It's not solving some other problem. So it's not making a prediction about what the weather's going to be next week or what kind of material should be synthesized in order to have a much more efficient engine, for example. The quantum supremacy is the beginning of the next step in whatever happens with quantum computing, but it's not the replacement for what we're doing here in high-performance computing.
Don't throw out your laptops, don't throw out your Summit supercomputers, your Frontier supercomputer just yet.
Right. The frontier of information technology is going to advance in many ways, but yes, it's not a drop-in replacement in any sense.
Thank you.
You're very welcome.
After we spoke with Dr. Wells, the journal Nature published the paper on quantum supremacy, but not everyone thinks Google really achieved it. IBM, which has its own quantum computing lab, immediately disputed Google's claim and published their own paper saying they could solve the problem specified in the quantum experiment in an existing supercomputer, and in far less time than Google was saying.
The authors of the Nature paper wrote that they used the quantum computer Sycamore to perform a series of operations in 200 seconds that would take a supercomputer about 10,000 years to complete. IBM, in its official statement, responded, "We argue that an ideal simulation of the same task can be performed on a classical system in 2.5 days and with far greater fidelity."
Okay, so the squaring off in computers today is not just between petascale or exascale supercomputers. It's also supercomputers versus quantum computers. Many media outlets have credited the quantum experiment to Google, but as we heard, Oak Ridge helped, and so did researchers from NASA.
I'm Eleanor Riefel. I'm the lead of the Quantum Artificial Intelligence Laboratory at NASA Ames Research Center.
Dr. Riefel is a co-author on the quantum supremacy paper.
It is a very exciting development. It means that we are able to do one thing faster on a quantum processor than on the largest supercomputer in the world.
And that one thing is?
That one thing is to generate samples from a random quantum circuit or a set of random quantum circuits. That is not a terribly useful thing to do, but it is a first step towards testing these processors, which will become useful for a variety of applications.
But what makes them faster? I mean, do they have, just faster electronics, or is it all smaller so it works faster? I mean, what makes a quantum computer better than the one I have in my phone or on my desk?
Yes, it's not just that it's smaller and uses quantum effects, but that we're encoding information in a new way that's based on quantum physics as opposed to classical physics. So we use qubits instead of bits, and then we have a wider variety of quantum operations. This allows us to create correlations that have no analog classically, and then we can use those correlations to speed up certain types of computations.
All right. Well, then finally, Eleanor, this is, supremacy. It sounds like a big step for computing. People have been talking about quantum computation for quite some time. I think the ideas go back to, maybe Richard Feynman, maybe earlier than that. And now it sounds like, the ideas are being turned into hardware that actually runs in a lab. Is this, the beginning of the quantum computing age? I mean, is that your feeling about it, or is it still just too early to know?
Well, it depends what you mean by the quantum computing age. If you're expecting this to be on your desktop next year, then no. But if you're expecting this to be where we see a blossoming of algorithms and a clearer understanding of what the long-term impact will be, I do view this as the beginning of an era. And this is a time that I've looked forward to since I started looking at quantum computing in 1996. And at that time, I did not know whether I would be alive by the time we got to the point where we had quantum processors that would be beyond the power of supercomputers. And supercomputers have expanded their power in that time tremendously, but we still managed to reach this milestone well within my lifetime. So I'm incredibly excited.
Terrific. Well, Eleanor Riefel, thank you so very much for speaking with us.
Thank you.
Eleanor Riefel is the lead of the Quantum Artificial Intelligence Laboratory at NASA Ames Research Center. Now, while quantum computers are not poised to be taking over anytime soon, We may be headed into a new era, as she said. And to learn more about what qubits can do for us, we turn one more time to Katherine Reilly.
So it is impressive, without a doubt. I think the direction that quantum computing is going today is very impressive, and it's very exciting, and it's very fast.
So the calculation they chose for this test and for the, if you will, the announcement, it didn't need to be a particularly useful calculation. It wasn't saying, hey, here's a compound that'll help us cure cancer or anything. It just was some sort of benchmark to prove a point.
That's right. Successfully using quantum computers to solve an actual problem is a breakthrough and is exciting and could really change how we're asking science questions when we're able to move these right into a more useful general purpose kind of role.
Okay, so it certainly sounds like, if you will, a quantum leap. But, people are always asking, what the heck is a quantum computer? I mean, it's nice to have that Latin adjective there. But what does it mean? I mean, can anybody explain that to me in a way even I can understand?
So the best explanation I've really seen differentiating a classic computer versus a quantum computer is that a classic computer only deals with things that are on or off. It's ones or zeros, black and white. That's it, right? So absolutely everything that goes on a classic computer is this on or off, 1, 0, black and white kind of model. But in a quantum computer, you have a lot more complexity. You have a lot more subtlety. It's not just black and white, right? You've got relationships between things that might be on or off or not quite on. And so you can represent problems in a much more complicated way and get a lot more basically kind of done, right, within a smaller amount of space, figuratively, not literally.
Okay, so you're saying it's just going to be able to do problems that are maybe many orders of magnitude more complex. In other words, that would take more time with a conventional computer. It's a time saver. Is that it?
It absolutely is, and it also brings forward, right, some ideas of quantum physics, right, into computing. What's an interesting thing about that is that there are a lot of problems that we care about that are driven by quantum physics.
Looking into the future, and I don't mean next week, but, some distant future, I mean, are quantum computers going to eventually replace the kind of computers we have today, the ones that do, ones and zero arithmetic?
Honestly, I don't think we really know for certain. Where we are today with quantum computing is, one, trying to figure out how to build a quantum computer. But there's another part to that, too, which is figuring out how to ask our questions out of a quantum computer. Could you use it to word process? I don't think anybody knows. But also, could you use it to solve the exact same science problems today, all of them? Like, do we know how to ask those questions out of a quantum computer? We're not sure today. So that's another area of very active research and very active exploration, right, to figure out whether they actually would or whether they would be more of a companion, where you would have whatever the future evolution of classic computing is sitting alongside quantum computing capability, and they're working together to solve problems in ways you wouldn't have expected.
Katherine Reilly, it's been a pleasure talking to a human brain as opposed to a semiconductor brain. And I want to thank you very much for speaking with us.
Thank you for having me. Thank you.
Okay, so quantum computing. I mean, here's one way to think about it. Rather than following a recipe line by line, a quantum computer does the equivalent of doing all the lines simultaneously and with variations on each instruction, too. I mean, you quickly make lots and lots of cakes, and you select the best one.
Well, we've learned a lot in the show about the ascendancy of powerful computers, from petaflops to exascale to one day perhaps quantum computers.
And you know what impresses me, Molly? It's the fact that there's just no natural limit for the speed of computers, for their capabilities. And you might think, okay, at a certain point, they're not interesting anymore because there are no more problems for them to solve. Just not true. Understanding the subtleties of biology, understanding the subtleties of physics, all of that depends on faster computers. And just one last thing. In 1975, there was the Cray 1 computer, incredibly fast. I just worked it out. It's 0.0000002 petaflops. Nothing like the Summit.
Thank you to Jack Wells from Oak Ridge National Laboratory and Katherine Reilly at Argonne National Laboratory for lending their human-based smarts to this episode. And best of luck in your race to exascale. Meanwhile, we are going to get our zetascale computing episode into shape so it's all ready to go when you are. Well, thank you to the Super-est production talent. There is senior producer Gary Niederhoff, assistant producer Sarah Derwin, and operations manager Barbara Vance. I am executive producer of Big Picture Science, Molly Bentley.
Thanks also to financial support from Rena Shulsky David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit education and research organization whose scientists study the origin and nature of life. I'm the Institute's senior astronomer, Seth Shostak, and I hope that computes. Also, a big thanks to our listeners.
Your ears have been attuned to an episode of Big Picture Science called Supercomputer Showdown. And if you'd like to hear more Big Picture Science, well, we have lots of episodes in our archive, and you can find our archive at bigpicturescience.org. And you will find links to our guests on that website as well.
You may be listening to our radio show, but if you want BiPiSci to better conform to your gusto-grabbing lifestyle, why not subscribe to the BiPiSci podcast? That way you'll never miss an episode. You'll find links on our website to the platforms that carry us.